4.6, modeling with exponential functions. So these are examples of where we might see exponential functions in the wild, things that directly relate to things in the real world. One of the most popular is exponential growth. And this is when the growth has something to do with the time it takes to double some sort of population. So we're given some notation here. Our initial population is n naught. We're being told that if we're given some information about how long the doubling time is, that's going to be A. And then we have, the size of population at time t is this formula right here. And then we just have to pay attention to make sure that we have, what the units are on the time, because it might take minutes to double, it might take hours, it might take days, it might take years. So we have a certain bacteria. Didn't mean to gross you out, but here's a picture of some gross bacteria. We are told that it doubles every 15 hours. So every 15 hours, you have double the amount that you had 15 hours prior. We're also told that we had 500 bacteria in the population from the beginning. So we're trying to find a model for the bacteria after t hours. So being told that really tells us that we're just trying to write n of t with any of the values we're being given. And because it's going to be a model after t hours, we want the t in there. So really it's telling us that all we need to do is figure out what our n naught is, as well as what is our a. So if you take a look at the question there, you'll probably notice that we are being told that the doubling time is 15 hours. So I'll put 15 for a. We're also told the initial amount of bacteria, and so I'll put that in for n naught. And then I can just go ahead and fill those in to my formula here. So that's 500 times 2 to the t divided by 15. Okay, so that's the first part of the problem. So just know that's part A. So we'll use that now. Okay, so now the question is how many bacteria are in the colony after 50 hours? So I'm going to go ahead and write out what I just had, what we just figured out from the last question. Number 15. Okay. And then understand that it says how many bacteria are in the colony. So we should realize that we need to find t, because it's asking us for what is n of t. Basically it's asking us what is n of 50, because it's giving us a time and asking us to find the amount after that amount of time. So in this case, plug and chug. We can put in the 500. We have 2 to the 50 divided by 15. So you want to work to try and get that all in the calculator at the same time. 500 times 2 to the, you may need to put parentheses around the exponent, 50 divided by 15, depending on what your calculator does. You can do this in pieces, it's up to you. But if you put it in correctly, you should have 5,039, and then I'll just show you that it has a decimal here for 2. We want to round this to the nearest bacteria, so that just means the nearest whole number, and so we'll say about, so I'm going to look at the 6, it's going to tell me I need to round up that 9, so 5040. So notice it's closer to 5,040 than it is to 5,039 because of that 0.6. So about 5,040 bacteria, just a plug and chug. It makes sense because if the doubling time is every 15 hours, notice that that exponent, 50 divided by 15, is a little more than 3. So we're doubling it a little more than 3 times. And what that means is, it starts with 500. After 15 hours, it's now 1,000. But after another 15 hours, now it's 2,000. So it's doubling, from what it was initially. So do understand that it's going from 500, doubles to 1,000, doubles to 2,000, doubles to 4,000, doubles to 8,000, and so on. Okay, now the next question is how long? So how long should make you think of the fact that when you're looking at your basic example here, which is 500 times 2 to the t over 15. one of those things you have and one of those things you don't. So you either need to find t or you're given t. Well, we're asked how long. So that tells us we are trying to find t, the time, which means we must be given n of t. And in reality, that is true. We are given that we want to know when is the population going to be 8,000. So we are going to take a look and say, okay, 8,000 equals 500 times 2 to the t over 15. And then we're just solving this for t. So we're going to be using those things from the exponential equations section to solve this. The first thing that we'll do is just divide both sides by 500. Because of space, I'm just telling you I'm dividing by 500. If you want to write that down, obviously that is fine. We have 16 equals 2 to the t over 15. Now, a couple things you can do. You could take the logarithm here of both sides. That's totally valid. You could do log 16 equals log of 2 t to the 15th, and then use the power rule to bring it down. Another option, because 16 can be rewritten with a base of 2, you could solve it similar to another example that we saw. It's up to you. By doing that, we have 4 equals t over 15, because the exponents need to be equal. Multiplying both sides by 15, we have t equals 60. So that's a nice whole number. We didn't have to do anything too crazy there. So we would just say it would take 60 hours. It would take 60 hours. It makes sense because, like I said, if you start with 500, it doubles to 1,000, it doubles to 2,000, it doubles to 4,000, and then it doubles to 8,000. So realize that that's 4 times that it doubles. And since it takes 15 hours to double, it makes sense that it would take 60 hours to double 15 times to get 8,000 bacteria. It all makes sense. Okay, now this is exponential growth, not thinking about it as a doubling time, but just exponential growth, which uses e. So that's another common base. In the last one, you'll notice we used, we had 2 as the base of our exponent there, talking more about doubling time. But when we talk about exponential growth, we typically use that base e. So very similar to even when we saw it with continuous compounding, these have a relationship. Notice you're given the information, similar to some of the stuff we did last time. Probably the only big difference is we want the relative growth rate. We're going to need that information. And here we go. So suppose we have a city and it has a population that follows an exponential growth model. It was going like this. What must the growth rate be for the city to double every 10 years? Round your answer to the nearest percent. So we want to think about these 4 pieces. R, T. So think about anything we have or anything that we're trying to find. If you want to pause, you can kind of fill those in, whatever you're thinking, and then come back. So we're trying to find the growth rate, and we want to know after 10 years or in 10 years. And then we don't have anything else. We don't have anything else. But here's what I want you to think about. When you're being asked for the city to double every 10 years, all that means is, in 10 years, what would the growth rate need to be? You really just want to think about the fact that the ratio of n of t divided by n naught. So I'm dividing both sides by n naught. So what this is the initial population, and this is the ending population, after 10 years. So when you think about it like this, think about the fact that this ratio just needs to be double. Meaning, if the initial population is 100, the ending population is 200. If the initial population is 500, the ending population is 1,000. If the initial population is 6,000, the ending population is 12,000. But for any of those examples I just gave, the ratio of the 2 numbers is 2, or double. it's gone, it's doubled itself. And so because of that, we don't need to know what it is and what it's ending. We just know that it needs to double. And so that ratio needs to be 2. Then we were also given that the time would be 10. So we have 10 times the rate. Now it's time for some logarithms. Because we have e, the best thing to do to free that r, we are trying to solve for the growth rate r, is to use ln. So I'll use ln on both sides. And what that'll do is give me ln2. I'm going to just move it up over here for space. So I'll have ln2 equals, and then I'm taking that ln of e so that I only just have 10r. That's my goal there. And then to solve for r, I'll divide by 10. I'm going to bring it to the left-hand side so that it works. I don't know. So that I just like r on the left-hand side. So I'll have ln2 divided by 10. And that is some number. So we can put that in the calculator, ln2 divided by 10. And we see what we get. And it looks like you should get, if you did it correctly, 0.0693. Now, as a percent, that is 6.93%, multiplying that by 100. So because of that, we want to round to the answer the nearest percent. So I'm going to say 7%. That's actually a really high growth rate. You don't really see growth rates that high with populations, but you know, this is just an example. So the growth rate is 7%. And so that's an example of an exponential, but not a plug and chug, actually having to do some solving using ln. Period. There we go. All right, so we have a couple more examples, Okay, so another thing is decay. So you can have exponential growth, but you can also have exponential decay. So a common thing is substances that have a half-life. So there's a lot of things that when things pass, like say mammals, when they pass, when they die, there are substances in their body that start to, lessen. And because of that, there's a possibility of actually being able to do, that's how they do a lot of their, seeing how old something is. So we have something notice similar, it uses slightly different notation, but it's all very similar. And we have that if we have an initial mass of a radioactive substance, so m naught is the initial, then how much there is after a time t is modeled by this function here. So again, very similar. Notice the negative. We are talking about decay. So we have a flipped exponential. And we're given that r is ln over h. That's the relative decay rate. And so we're going to take a look here and see what we've got. Okay, so after 500 years, woo, it's a long time, we have a sample of a radioactive substance. It has decayed to 80.4% of its original mass. So after 500 years, find the half-life of radium-226. Find the half-life. So notice the half-life is h. That's what we're trying to find. Half-life. How much? So when we think about this function, let me put m of t and then m naught, so I'm just going back to the original, e to the negative rt, but r is ln 2 over h times t. So I'm doing that because we're trying to find h. So I need to get h in there, but that's what r is for finding a half-life, ln 2 over h. So now I can think about what else I have. So after 500 years, that's a very long time. So after 500 years, we've got 500 for t. And then this is similar to the last one. So instead of saying, oh, something has doubled, what we know is that it's decayed to 80.4% of its original mass. Why do I keep wanting to say mass? What that means is when we divide what we end up with divided by what we started with, we should have 80.4% or 0.804. So very similar to the doubling, but notice it's less than 1 because it's actually a decay. It's going down, it's going down, it's going down. So we end up with the fact that if we divide both sides by m naught, we should get 804. And that's negative, and then we still have our e. Let me move that down a little bit. E and then to the negative. And then we'll be able to start using some natural logs. So we have e, I know this looks like a little bit much here, but negative ln2, ln2, and then we do have t. Let me think, how can I write this a little bit easier to see here? Okay, so we know that t is 500. So one thing we could do is I could write negative 500 times ln2 over h. Maybe that's the easiest, maybe that's a real good way to see it. Then if we take the ln of both sides, we're trying to free the h. In this case, we want to free the h. So we've got an e, we're going to go to that natural log. So 0.804, and then e to the negative 500 times ln2 divided by h, and then that frees my exponent. So now we have this ln 0.804, just some number, but over on the other side we freed the h. So we have negative 500 times ln2 divided by h. So now what we can do is just a little bit of algebra here. Time-wise, things are a little, like my space here is a little bit wonky. So we can multiply both sides by h. I want you to notice that. So I can multiply the left-hand side and right-hand side by h. So it's going to bring it on the left-hand side. And then if I divide both sides by ln of 0.804, it'll bring it to the other side. So I'm doing this in one step due to space, but what's happening again, I'm multiplying both sides by h, but then I'm dividing both sides by that ln. And that isolates my h and gives me just a number on the other side. And if we put that into the calculator, what we're hoping for is what we're looking for, the answer, which it does. We get 1588.65. And we're being told to round to the nearest year, so it's saying half-life. So the half-life is 1589 years. So what that means is that it will take almost 1600 years to get from the amount that it started with to half that. That's what we have found with all this stuff here, is the half-life, how long it takes to be half of whatever it started as. So now that we know the half-life, we can write m of t equals, and then we have our m naught times e to the, and then understand that what we have now is the negative ln2 over 1589, because that's our half-life that we found h. So that's our half-life times t. Now we can plug in any other information that we are given in this example, which is we have an original amount. What else do we have? We have some time, 3,000 years. And so now it's just a plug and chug. Yay, yay for plug and chugs. So 250 e to the negative ln2 divided by 1589, times 3,000. So really see if you can get this in your calculator. There's a few pieces here, so do the best you can you can do it in one step, multiple steps. Understand that this whole thing is the exponent, so you do need to do that whole exponent and then e to that thing. So make sure you can make that happen and see what you get. And hopefully what you get is maybe smaller than you thought, which is 67.5462. But really, I mean, it's been 3,000 years. So this, whatever we started with, is going to get smaller. So we can say about nearest tenth, so about 67.5 milligrams after 3,000 years. And there we go. And that is section 4.6.